Alright class, this is the lesson on differentiability. Basically, can you take a derivative at a certain point? So there is no derivative at a point if the quotient f of x minus f of a over x minus a fails to approach a limit. So these are the different things you can have when you do not have a derivative at a point. You can have a corner, which means that the one-sided derivatives are different values. I'll write that into. They're different values. An example of that can be a y equals absolute value of x graph. Oops. So if I want to, I don't know why the eraser's not working. There it goes. Alright, so y equals absolute value of x. So if you graph that on an axis, you get this graph. And sure enough, you guys should know this since they're lines. The left-handed derivative coming from the left. If you come from the left, the slope of this line is -1. And the right-handed derivative for this one coming from the right is 1. So because these are different, you have a corner there. Even if one of them's a number and one's infinity, you'll still have a corner. Now, a cusp basically means that the slope of the line as you approach it, the secant line or tangent line, if you approach the point, the slope approaches a vertical line in either direction. However, one of them is going to be negative and one of them is going to be positive. So what that looks like is this kind of equation. Now, I'm not going to, that's what an example of an equation would be. Now, this is just a random graph. So I'm going to kind of shift it off center here just to show you what it looks like. So a cusp looks something like that. It almost looks like a V, but it's more curved. Because if you think about it, as you approach this point, the slope of the tangent line or the secant line here is very, very positive. So it approaches positive infinity from the right. If you're taking another tangent or a secant line here, going through these 2 points really close, notice how I'm barely touching the line there to the left of the point, even though it looks like it's going through. This is a very negative slope. Okay? So, because if one of them is positive and one of them is negative infinity, you have a cusp. Now, if both of them are either infinity or both are negative infinity, then you get what we call a vertical tangent. So we have y is equal to the cubed root of x is an example of that. And I'm going to exaggerate this graph so you guys can see what I'm talking about. Just any graph that is a cube root function will have that, and even that is not the best example because it should look more vertical here. At this point here, yeah, I'm going to actually make that a little bit better. Something like that, okay? At this point here, there's going to be a vertical tangent, so we cannot take the derivative at that spot. But notice how on this graph, as you're approaching it, we have a very positive infinity slope, and from the left, we still have a very positive infinity slope, okay? So because these are both the same, that's what gives you a vertical tangent. And then finally, a discontinuity. You cannot take a derivative at something that's not continuous. That could be anything, a jump, or a removable discontinuity, or a non-removable discontinuity, or an infinite discontinuity. You can't take derivatives at any of those places. Alright, so this example, find all points in the domain of this absolute value function where f is not differentiable. Well, again, knowing our absolute value curves and equations, you should note that this vertex is at 2, 3. So there's our vertex. And since the slope is 1 and it's positive, it's going up in both directions with slopes of 1. Again, from the left, this actually is a slope of -1 for this line, and this line has a slope of 1. Since both of them are different values, this would be a corner at this point. So it's corner since the left-handed derivative and the right-handed derivative equal different values. Okay. All right, so that's a corner. Now, there might be time. Oh, I also have a little blurb here about if a function has a derivative somewhere, you know it's continuous. However, the converse of that statement is not true. You can't say if a function's continuous that it has a derivative, because it could be a corner or a cusp. Because you know you can't take the derivative at a corner or a cusp, but it is continuous at a corner and a cusp. All right, so now we're going to show how to prove that it's not differentiable and figure out what kind of what issue we have that makes it not differentiable. Is it a corner, a cusp, vertical tangent, or a discontinuity? Well, since this is just x to the 2/5, there's no break in that graph. There's no vertical asymptotes. There's no zeros on bottoms of fractions. So already we know that this is continuous everywhere. So it's not going to be a discontinuity. And you could always check that first, because that's not a derivative test. That's just checking continuity. So here's what we do. We're going to do the left-handed derivative first, which is equal to the limit as x approaches 0 from the left. And remember, the formula we use is the function minus the function at the point, and the point here as 0. So the function is just x to the 2/5 minus, when you plug a 0 into this, you get 0 over just x minus 0. So we get the fraction, the limit as x approaches 0 from the left is 1 over x to the 3/5. And again, this is a vertical asymptote, so that means that the derivative is approaching infinity or negative infinity. If you're coming from the left and you put a negative number in here, it stays negative because you have a fifth root and you're cubing it, neither of which will do anything with that negative sign. So that means that the derivative approaching from the left is a negative infinity. The right-hand derivative is the limit as x approaches 0 from the right, and it's the same thing though, same difference here, same formula. So we get the limit. The only thing that's different is we're approaching from the right of this function, and as we approach from the right, we're putting positive values in, which means that the slope will be positive, and as you get really, really close to 0 on the bottom, 1 over 0 is pretty much infinity. So we have one of them is negative infinity and one of them is infinity, and if you guys remember, that means you have a cusp. Okay? Now, just real quick to check, x to the 2/5, I'm going to graph that so you guys can see what that looks like. Now, obviously, with the proving, you might have this on a non-calculator portion. Oh, I don't need that there. Okay, and it's going to be at 0, so I'm going to window just from like -1 to 1, and then the y is probably only going to be like -1 to 1. We'll make it a really small window and see what that looks like. Alright, so there it is coming in, and sure enough, right at the end, you see how it, from the left, you have a slope of, it's vertical, but it's negative, and then from the right, it's vertical, but it's positive. Therefore, that is a cusp. Okay, good. So that is the lesson on the different kinds of differentiability, or things that are not differentiable. And yeah, you will have to prove one, so make sure you do those problems, and I will see you next time.